that don't squeak. Like, my dress shoes don't squeak. Both my tennis shoes and the boots I've been wearing make a squeaking noise. And I don't think I'm the only one, but I hear it mostly in my head. So I think I always feel like when I'm walking down the hallway, everyone's like, oh, here comes Dr. Tao. It makes me self-conscious, I guess. But I also feel like it's a defect of the building.
And I just gotta embrace it and get those like little kids' shoes they have in Japan. They're just like ducks that squeak when you walk.
The shoes they have in Japan.
Yeah, they're like little kids' shoes. They're like ducks on them, and they squeak when they walk. Just gotta embrace it and get rid of those.
Luckily I did.
Switch between accounts on Discord.
Yeah.
So, how you doing?
They actually got us on the meeting early.
Right?
They actually got us on the meeting.
They took your mind. seats are there?
Five minutes.
For some reason, I thought it was 25. That's when it ends, isn't it?
It's from last class. All he did basically was just prove the best limit. Pretty interesting, but I don't know if we're gonna need to know the actual proof of the best limit.
And maybe it'll never work again. Oh, hey, it worked. Takes a long time, but it works.
6 a.m. Yeah.
Oh. I'm not trying to get drunk at 6 a.m.
Close it down at 2 a.m. Go back at 6.
Sure they have. Chapter. Basically, he's just mathematically proving why the best limit is.
I believe it. See you over 27.
Oh, it's not
Good news.
Thanks.
Don't we start quicker?
I have a question. If you were to get a boat, would you put a wind propeller on it, or would you just put a sail on it?
I don't think you can hear us.
Can you hear us?
No, I can hear you, I just wasn't 100%.
It was to you.
Okay.
Wait, are you referring to that?
Oh, great.
As
As soon as he starts talking, it cuts out.
Has like the.
Yes, I know.
Yeah.
Are you talking about like
What about the magnets effect
propeller,
just
or
big
what's it
cylinders
called?
that spin?
What they have on the bayou?
Actually, no, I am talking about that exactly.
Yeah. You should ask him
I
about
don't
it.
even airboats.
Is that what they're
Yes.
called?
We can't hear you. Can you hear us?
We
Your
love
feeds cut out.
lifestyle.
Yes,
Oh,
Should we just like
yeah.
throw a phone downstairs that says
Have you ever
front
been on
desk
there,
fucking fix it?
I hear it loud.
Yeah, they're loud.
I can just start playing
You know?
golf. That'll make it.
Yeah, you go fast because it's a flat.
Oh, literally, we went to a room that was empty. Said it was
So
open.
you
You
just-
just start playing
you
golf.
see an
For some
area.
reason, the computer just shuts down.
I wonder if you could put like,
And they update something.
you know, like
And then
the
the guy takes over for a second.
paragliding stuff.
Yeah.
And that's all that motor is. It's just like the exact
So,
same engine.
Julia, when did we
color
take
used
that
by, like,
color
paragliding.
quiz thing?
So I wonder if you could get a bigger chute, if it would have enough lift.
Oh, it's supposed to be big.
Yeah, he just.
I saw a video of a guy
Okay.
who used it
So,
saying,
okay, and I never got to see people.
forgot what it was. What
Hmm?
he did.
You miss out on something?
But he used a band that basically like flying McDonald's.
The chapter, when did you come back?
Any cool?
Last, way back when it was closed.
Oh, the Paris Street?
Yeah.
No, so it had a greater velocity. See?
I don't think we had
he
planned
had
anything
was a
for it.
parasail and a fan on the top. And he used that to like, it might have been something else though.
Sounds nice. writing it down. I'm gonna be like, no. See if he.
No. No.
He's gonna be, what the fuck?
Oh. You're looking stupid now. Bet you look stupid now, Yulia.
No, Andrew.
That sounds
That's
good.
even worse.
Yeah. No, me?
We don't do anything.
I'm okay.
Well,
I'm just
I'm home.
saying. What's up?
Hello.
Oh, I take the jacket.
I think they realized they're up. Probably.
Oh, no, he just was there. He
Hey,
disappeared.
Brendan.
Why does it always zoom in on this?
People's not coming anymore?
Huh?
Are people not coming anymore?
I don't know. Maybe not on. Was it like this on Wednesday too? Maybe not. Work weekend. That's a big ass backpack.
I got to carry my 17-inch laptop.
Wow. That's too heavy for my back. Like a child. You're carrying a child on your back all day.
But now I have a small laptop.
Oh, that's good.
I don't think they let people into the games. with-
You go home now?
Yeah.
Because it's televised.
Just go right back.
Oh, no, we had it 2 years ago. We had, actually, no, I think it was freshman year. We had, they let people with signs in
For game day.
for the USC game.
Because that was game day, right?
Sam,
No,
where'd you go?
not, that was Ducks.
You wanna
Hello, lovers.
It was Oregon.
97.
You skipped on.
I fell asleep.
Skip twice.
Oh, why not?
And there's homework to do.
So you just want alcohol.
That's homework. This slide.
You just do it. You just, there your body.
I just woke up.
Yes.
I don't.
Don't put fucking.
I don't
This guy.
know.
This guy no pressure?
Damn it, he's back.
That was.
I don't care.
Where's the window?
Couldn't find a
That was
person
fireworks.
who knows what we're doing.
Holman, hello, Bremerton.
Hello!
Hello. So I heard, hello. I did hear the question about sails versus propellers. I didn't understand exactly what you were asking. And
He was way too.
when, from our point of view, you guys like stopped moving.
Same.
And froze up.
We can't see you.
Okay, wait, you can't see me now?
Oh, they see me.
No,
Nope.
your class.
The
Class,
last
your
year.
class and the projector.
Oh, you see the glass. All right, well, they're a good looking group.
Say for the most part.
I was not the
We
one
do have
who
a guy
said
that you
that. I don't know who said that. I was not the one who said that.
Not in ours.
Okay, I can
Come
see,
on.
I can see that you can see me now.
Yes.
Yep,
Yeah.
okay.
Alright, and I am gonna try, because this was bizarrely working before, where I actually said, so dot cam, media share, can you see my dot cam?
No.
No.
No, alright. Give me 1 second. It likes to warm up.
Oh, really?
Actually, I'll turn it to local PC media share. Let's see. Oh, sorry, recycle this button.
Did you want to put someone with a bag on yesterday's notes?
I mean, it seems like this was working right before the calls cut off, where I needed to share here and see what they're seeing and what the users there were seeing.
Chocolate chip cookie.
There you
I think I still have this issue for
See the cookie.
myself.
My homework is really
Still pissing some others off. And they're like, go back.
Should I rephrase my question in the meantime?
I can't think about your question and try to get these things. I'm not good at multitasking like that.
No worries. Your trash cans on here.
But do you have any idea of anything else? And it just looks like it's-
I didn't think I could.
So they're seeing it.
Ah, okay.
So the students here are seeing it. I think those monitors should be showing the local PC. Yeah, and I actually want it right now when it's at the dot camp. But
So what's the forecast?
Shitty.
that takes a second, but it will switch to dot camp. That looks like something on there. Because they have the same thing on there 3 times. Yeah, but it was working before. I mean, was able to see on their end. I was seeing my content on the big monitors, and the little TV screen, I was seeing me. So,
It's like there's somebody who's on there trying to figure it out.
well, actually, wait. So, Bremerton, are you seeing content? No. No, so neither Bremerton nor Pullman is seeing the content, so I think it's something on our end.
It was working earlier and then it stopped.
Yeah, wait, was it working earlier before the call? You mean before the call cut out?
Yeah.
Yeah.
Well, what?
Yeah. Agreed.
Oh, no.
I want to use both the document and the computer today. Which is the first day I really want to do that, but I want to show them some stuff on the website. And I want to show them. The good news is the derivation I wanted to go through today is a lot shorter than the derivation I went through on
Okay.
on Wednesday.
I was slightly sad that more people got ready.
Well, I just never.
When
got
did you
to
do
inter-
it?
Well, I never, I met him on, didn't meet.
Okay.
I'm sad. I was like, fuck, I'm not blind.
If I had to guess from what he said, I'm probably a hybrid of red and blue.
I feel like you'd be like, you don't seem like you seem more like yellow though.
Blue, yellow.
You don't seem as like aggressive. I'm slightly, I was.
Okay, well, the tech guy is going back into his office and he's going to try to something on their end. So anyway, so now that there's nothing for me to do, you want to rephrase your question?
Yes. Would you rather have a sailboat with a sail or a turbine that spins opposite to the wind direction? Like you're trying to go into the wind.
This is kind of on YouTube.
I think you need to explain the video.
So, I don't know the answer to that question. I mean, first of all, I'd rather stay on land. But, I'm kidding. So, I know there was an ongoing thing on YouTube about, it wasn't a boat, but it was a car, and they proved that you can make a car go in the wind faster than the wind speed, which somebody was arguing was
It's not possible.
it's not, like a professor was saying it's not possible. And I don't like it. They said, a YouTuber said it was possible and the professor said it was impossible. Actually, some other professor said it was possible. The YouTuber wanted to see which professor was right.
But you kind of knew already.
Yeah, but kind of knew, well, I didn't know he necessarily thought it was two physicists disagreed. I don't know who's right.
I thought he had already ridden in the car and gone faster than the wind speed.
I
Then they had that argument.
So I watched the first half where they tried to, and they had mechanical problems.
Okay.
And so I think that because I saw a bunch of videos. I mean, is that what you're alluding to? Because the answer from my point of view, I mean, which is better if you're going to go into the wind? I know there's a way with sailboats that you can tack and go back and forth. And which is better, I don't actually know.
Okay.
But I have seen the YouTube video, if that's what you're listening to.
I have
Yeah.
not seen that. Sounds interesting.
Actually, are there sailboats with solid, with solid sails instead of?
We're talking trying.
There's also some really cool ideas for sailboats that, they use something similar to a vertical axis wind turbine. They use something called a Flatner rotor.
I know.
That's not the reason the sailboat is working with.
Instead of sails, which are kind of.
Should show us that video of skydiving.
So, skydiving? Oh, while we wait, I can't, because I could only show you, because I can't share content.
That's okay.
So I have a question.
Yeah,
What are the more like sustainable ways of disposing wind turbine blades? Because all I've read about have been like that they're showing up in landfills and things like that because they can't be recycled, or that they're meant to sustain so many forces and therefore they're harder to manage afterwards.
yeah, that's a really good question. And it's not, there's not a simple answer. So, not every wind turbine blade is made the same way. But since that has become an issue, there has been a lot of research into the existing blades that have already been produced can be recycled, and research into how to make blades in the future so they are more recyclable. And I think that kind of question and that kind of issue, I mean, it raises a big point that I kind of hold dear to my heart, which is when there's anything that's really becomes very politically charged, like wind energy or renewable energy, there's always a way to, there's always positives and there's always negatives. And there's always a very quick, short way of pointing out a negative. So it looks really bad. And just assume that people who are pro wind energy, and the same could be true with nuclear, right? That the people who are involved in it aren't doing anything about it or don't care or aren't aware of this. The fact, so wind turbine blades not being recyclable is one of these issues that it gets a lot of press. And in fact, I did a talk last year on wind energy and the environment. And at the time, that was like my last slide, because it's an example of somebody did a study, somebody noticed this, and then suddenly in dozens of journals and newspapers, there's articles about the same issue. And what happens is the people in the wind energy industry who care about the environment or care about recyclability, they're aware of this issue. They are working on it, and they are working to improve it, and they know how big of an issue it is. And there has been a significant amount of dollars put into, and research groups started up to study this exact issue. I think bird kills also falls into this category, as it's an issue that it's a con for wind energy, and it's a con that gets a lot of attention. But oh yeah.
We're gonna try and restart the call.
Okay. Okay, guys, be patient. We're gonna try to restart the call again. I apologize for this.
Okay.
No, it's fine.
You're good.
Bye for now.
I read somewhere.
Goodbye for about 3 minutes, hopefully.
Bird kills aren't an issue if the birds are actually all government spy drones.
There you go. Well, you can just turn them off during migration time.
Yeah, so you can go down.
It's not that big.
Yeah.
People are just. there's always gonna be downfalls with every solution. So
Yeah, it's hard though
it's
when people are.
continual
It's like
improvement.
one of those things where it's like technically carbon is used when we make solar panels, but compared to everything else,
Yeah,
it's still.
it's like batteries.
So people are gonna be opinionated and find something they dislike about it anyway. Because
Exactly.
like one of the
They
things is
already
that
have
like, well, because one of the things
Okay,
like,
so should I try to share content?
There's no
Well,
science
it still
backing
says it's media share.
dislike it because it ruins the
It doesn't.
skyline. And there's nothing behind that.
From it, I
It's
think it was
just
already
hard
saying it's
to
sharing
not
media.
dissuade anyone from that personal preference.
Yeah.
Not typically anyway.
Same thing with hydro.
That's a huge problem in
Yeah.
Hawaii.
Yeah.
I mean, it's the same thing with hydro. Get 80% of our electricity hydro annually billed.
I make a suggestion.
None of my damage to the fish is all.
Yeah, well, but if you see the pattern, the salmon aren't migrating this far into Snake River.
They're the same.
Yes, it would be the same. Otherwise.
You know the Japanese still whale hunt?
Yeah.
Or they're able to come up with designs for hydroelectric, but now they want to fire a dam.
They would
Did
not.
you know require a difference of like 2 or 3?
Unless he make a bunch of.
I forget what it's in Finland, but
Yeah,
somewhere
with our
there's a
friends,
nuclear reactor,
whales.
and since the way the water is run, the part that cools the reactor isn't what's put to this other
Do that
water.
with whale hunt.
That's not correct.
The water they use to cool the really hot water
Can you power?
doesn't actually touch that water. And since that's true and it still gets to a high temperature, they just shoot that up to people.
Is it more heat exchange?
Exactly. So it just automatically heats up the water and they just send that straight to the housing area. It's just free hot water.
A lot of the big ships
Oh, here's
nowadays.
another thing, why don't they
These will
put
get
nuclear
it.
reactors in the ground?
That is a new design that's modular.
So the hard thing is when you tank containment, so that.
Well, I mean, yes, you
It's
were.
actually exposing the waste underground.
Yeah. But the issue, so look at, well, the reactor, but
Because if the reactor.
it's still that containment factor that they need. And if, what if, the other issue is if that blows and then you have a giant earthquake or something, that could cause a rupture, tectonic plates.
Everything.
But
Depending on
the hazard is there with the nuclear reactors, plus there hazards to the.
Different types of like
of-
materials. Have you ever seen how you can look at drills?
Let's look at this
So-
one.
That's not the medium, but essentially. You
Think
use
about
that as demonstration.
Yeah,
Concrete
yeah.
and metal and stuff
Yeah.
like that.
Start talking
But
about.
the whole
Yeah,
cotton mill.
but just
in
how
that
many
sense, yeah.
layers
We're
and
gonna be able to
that
do that.
resistivity
Like,
to the, or at least to stop the gamma.
fire
That's like in for Negroes
Light
and
it
has
off.
tanks, I don't know if you know much about them.
light up from the close fist.
But they have,
You said you're watching your kitchen.
yeah.
Oh, yeah, no.
Yeah.
I
They
would
have
say
waste
it's
containment
more
tanks. They're having
because
issues
if
with
we're
erosion.
into the reactor, they also are
Something, I'm not sure. Or else if it's just wasn't taking oxidation.
just feel just like.
I'm liking that, I'm liking that idea more and more.
It's just so hard research.
But he's saying.
Feed it with a large object.
It's like canceled glasses.
And your remote's not working, you can hit it really hard.
Yeah, yeah.
Always fixed.
Yeah, I just got asked for summer to my senior.
No way.
This is gonna work, this is gonna work.
I will say, when I hear something, I knew it was
Yeah, sure.
So then we put a.
Hey, incidentally, remember in, this turbine, I was saying I had nightmares about my husband?
That was the wrong class.
It was a long This is almost exactly the nightmare.
Wow.
These are how we're. Alright, so.
At least it's on the house, so just translate it over.
It's actually like.
Microsoft connection.
Oh, that's cool. Oh, okay. Oh, that's cool though.
Sure, convince the US to go to space, not convince the US to go more into
Well, we don't need to convince the US.
Yeah,
the private sector is still building gas. Not proven that there's more, return. We build gas and natural gas.
Oh, I don't envy you.
Natural gas is gonna help
with the layout.
Yeah.
Well, it's not.
Yeah.
Give it already on 20.
It's
They're making electronic
Yeah, we're
software.
very quickly.
How we just-
I'm not saying that.
That investment.
So, since we still have like a bunch of shit that have unknowns.
Yeah, that's it.
I was like, we just went like yesterday.
We're paying money to eat.
Have the moon be the, have the moon technology.
More like the exact reason why we should put anything that we don't care about on there.
No,
No, my rationale is.
Why should we burn natural gas there?
because.
There's no oxygen there.
Besides
Exactly, you can't.
we could burn coal.
Yeah,
There's no
there's no
environmental-
oxygen.
Let's not
The whole-
destroy,
The whole.
if we don't have a moon, then we don't exist as.
Well, just because we have to use like higher concentrates of oxygen or something.
Just because you have to require some of that stuff.
Oh, yeah, I know.
Yeah, I guess.
And if you have to reach.
I'm not terribly.
But, yeah,
This guy uses jug.
You're gonna come to
The only thing doesn't sell your services, third party. I was just saying, like, I'm not delusional, like, I'm pretty sure they still do.
It's just not as,
That's better than.
All on a Tuesday afternoon.
It's a search engine.
Actually,
Drive 5 minutes and work for a half hour.
So, the guys that
You are the product.
now I remember like.
What are you talking, when did this come on?
I have a great idea to pass the time.
Go up, go up.
Yeah. True, man.
Have you searched up
No, we haven't. That's not. Where's Elliot?
Or October or something.
That's it, probably just need.
They estimate that that's one thing that life could survive after all this starts.
Did we do anything?
Yeah, if they built a license for run a black hole before storage,
Yeah.
very last.
Probably a little more to
So we're.
Say like $60.
So it would be.
Yeah, I heard
Yeah, I tried to get that removed.
Yeah, of course.
Oh, good, my gosh.
So, one little piece of class business I can take care of while we're trying to sort this out, and we might, we might have to try a different room, is one of the ideas that came up. But in the meantime, the one piece of class business thing I wanted to discuss that I can discuss without sharing content, is I posted a new homework assignment. That's due next, I posted it Wednesday evening, so it's gonna be due next Wednesday. You're gonna look for a room, okay. After I posted the homework assignment, I decided to make one very small change to the homework. And it's on the last problem. So if you've already downloaded the homework, you might want to download the PDF again. The only thing I changed was in problem 6, which is the last problem. It says to, the original way it was phrased was, you're supposed to create a Weibull distribution and a Riley distribution. And then compare it to what the actual data, the histogram of the actual data looks like. And the original version of the problem said, standardize the normal distribution appropriately. I just added a little bit of text that says, because we selected our bin size of being, our bin size is bins of 2 miles per hour, that whatever, when you, the formulas for the Weibull distribution or the Rayleigh distribution, you have to multiply by 2, okay, before you compare it to the data set. Also, on those last 2 homework problems, do not wait till the last minute to do this homework. I'm expecting you guys will probably want to do those homework problems using Excel or some type of similar data processing application. And you might have to do some digging and some, okay, how to create a histogram, how to make a Weibull distribution in Excel or a Rayleigh distribution in Excel. There's functions that are built in, or you can just type in the formulas by hand. And there might be something where like you need to ask for some help. Also, the last question, you're supposed to find, using a Weibull distribution, how much power this particular wind turbine is going to create. I'm not expecting you to do that analytically. You're welcome to try. But I'm expecting you to use like a some numerical method. And again, you can use that, you can do it in Excel, okay? So, but anyways, I have a feeling that I definitely know this homework is beefier than the first homework, which is kind of a warm-up homework. So it's not a, let's start it an hour before it's due. And again, we're just gonna be kind of in a holding pattern until we're told wet room, and we're gonna try. Or I could just keep pressing this button and see if it magically starts working.
You know,
While I'm waiting for
tidal energy at all?
be told what room to go to.
Why is looking at this?
So when they're not. If the
Why
plane's
the
waiting, if the plane's waiting to land, it just plays the whole thing.
I mean, it's 5 o'clock on Friday, there can't be that many classes going on right now.
Yeah, because I read some of the US before.
Oh, okay, we started.
That's like saying we just one school.
Oh, yeah, so he made an endorsement to the vets to the Cornell.
It doesn't, because there's a lot of things. They have to give me. Freeze up all the codes, which I'm not gonna do.
Yeah, that's limited to sort of that.
Oh, I see, he's setting, it looks like he's setting us up in another classroom, so we can just walk down there. That's the other classroom, that's not us. So I think he's gonna come here and
Is the IT guy doing the lecture now?
he's gonna come back and tell us what classroom to go into.
What?
35.
I know it says 35, we don't have a classroom 35.
358.
Oh, it's 358? How do you know that?
It says, that's the name of the title on.
358, okay.
Cut off.
All right, give us about 10 minutes to get there. Not 10 minutes or more. It's not, we don't have that. We don't have more.
Yeah, exactly. That's like directly above us.
They were one of those tiny offices.
They've all just driven over to Edward.
No. We're all the same.
Yeah, everyone is like, work hard or something.
They're making.
There was a leak.
Keep it in there. Except for the.
You really, it's a James Bond.
It's a James Bond feeling.
I guess if something goes wrong.
That's a pretty.
I mean,
Okay, if you look at the coast, how much of it is
But here's the
He's left it.
If it's late.
Because the one that they tested there doesn't even, you can't see it. 'Cause it's all
Oh, so you need to make a new data set.
They benefit from geography.
See what it
This
does.
is nice.
Okay, okay.
And this is like actually go before. If they have a little thing to try and stop the water.
Yeah, same with Florida.
Florida's doing that?
Yeah, Florida's like, it's really
There's
football
some
fields
What?
worth of
Do you have
land.
anything lined up?
Not as gay,
No.
but and one or two.
Summer just ended.
I mean,
You know what the
that's
career
next
fair is?
summer.
October 4th.
How do you know that so fast?
And just.
I don't
So
know.
that's not what it is.
Okay.
Well, business people who don't care who lie.
You know, when it works on two.
Yeah, the majority of already.
Whose hand is that? That's
I'm
weird.
very confused.
Who is
I
that?
think he's sharing screen.
There's a lot of people.
Okay,
There's a lot of business.
Oh, it's the teacher's hand. Oh, okay. I didn't think that was kind of different. It's a fishbowl. Yeah.
They are seeing contact.
Okay.
Bobby, where's the
Alright,
kit?
Okay, well, I wanted to, my original plan, hi guys. Bremerton, and Bowling, you guys can see me, and you can see content, well, there's no, I don't have anything, but
Yes, we see
you
the
can see
picture.
content now, okay. I wanted to show you guys some websites and finish our conversation that I skipped. There's a couple of things I wanted to talk about at the end of chapter 2. And I'm just gonna hold that off until next week so we can talk. I'm gonna do a derivation today. What's on the syllabus is last time we discussed what's called 1D momentum theory. And so when we came up with 1D momentum theory, the big payoff with 1D momentum theory was that we got the Beck's limit. And we learned a few other things too. The thing with that theory, that 1D momentum theory, is it completely neglects the fact that the air behind the rotor is not going to be going straight. Okay? The wind causes the turbine to rotate. And there's this law called, named after a real famous British guy, Newton's third law says for every action, there's an opposite and equal reaction. So if the turbine is spinning in one direction and it wasn't spinning in that direction before, that means the air has to be spinning the opposite direction. Okay? And we've neglected that. So the goal for today is to account for the fact that the air in the wake will actually be rotating. And the book has a nice picture, which I should have taken out just to kind of demonstrate this. This is the air coming in, this is where the turbine would be, and then the air starts rotating as it leaves the turbine. Okay, and I also have some like really cool CFD simulations that I can show you that demonstrates that as well. I think I said somewhere will be posted on the will be posted on Canvas, and I haven't posted them yet. So I'm going to go through this derivation. Before I do, I'm just going to refresh our memory about this notation that we were using last time. So upstream wind, right in front of the turbine, right behind the turbine. I've already proved to you that that has to be the same, so we're just going to use U. Density, area, might have subscripts, pressure. We've learned what the induction factor is. We know what thrust is, what I mean when I say thrust. We know what I mean when I say power. Q is for torque. And this is the new stuff. This is the stuff we didn't use yesterday. Or I think we used capital omega yesterday, but now lowercase omega. So capital omega is the rotational velocity of the rotor. Little omega is the angular velocity of the wind behind the rotor. Okay, so the wind causes the rotor to spin, the rotor causes the wind to spin. Okay, and we're going to start using A prime as the angular induction factor. That is, it serves the same role in rotational velocity as A did without rotational velocity. Lambda is the tip speed ratio. And what we're going to have to do is we're going to have to look at, because the blade velocity is different close to the hub and further away from the hub. We not only need to look at the tip speed ratio, but we also need to think about what is the speed of the blade at some particular distance from the hub. Okay, and that's the local speed ratio. All right, so we're gonna start with a blank sheet, and I think I can do this in an hour, and I'm sorry, in 40 minutes, which is all the time we have today. So what we're saying is, so now what we're gonna look at is a horizontal axis wind turbine with wake rotation. And so there's a certain amount of kinetic energy in the wind. The kinetic energy in the wind is 1/2 rho A, and now I'm talking about energy, I'm not talking about power. So the energy in the wind is 1/2 rho A, the wind velocity squared. Okay? Now, this, by conservation of energy, must be equal to 1/2 rho A, the wind velocity in the wake squared, plus the kinetic energy in the rotor that we've transferred to the rotor. However, we also need to account for the kinetic energy that's in the wake, not because of axial velocity, but because of rotational velocity. So the kinetic energy in the rotational flow behind the turbine. And ideally, we want this to be 0. Okay, but it's not. Now, let's think about this. I have the rotor gets its power from the wind. So the power in the rotor is equal to, and I'm using the symbols Q, capital omega, which, to refresh our memory, is this is torque. Times angular velocity I said of blade, but I'm gonna, in my note, but I'm gonna say of rotor. Now, this torque is required for the blades to spin. If there is no torque, the blades will not spin. I'll say to get blades spinning. And remember, I also need torque for my generator. My generator will need torque. So ideally, I want to match this torque with the torque my generator needs. Oh, thank you. All right. Now the thing is I can get the same power. Now let me say something else. All right. So, the torque, the generator, the turbine, the rotor, is the one saying about safe correct? Say this power rotor has to equal power. Yeah, I'm gonna say it like this. I am gonna say it like this. Torque on rotor. It gets that because there's also torque, but it's negative. Torque on wing. Okay, so it's the torque on the wing that it's the fact that the rotor needs torque. And it's getting that torque because the blades are imparting a torque on the wind, and that is equal and opposite. Okay, now I have power, and that power, it could be equal to a little bit of torque and a lot of speed, or I could have a lot of torque and a little speed. Okay? The more torque that is applied on the rotor, the more torque I need to have applied to the wind, which will make the wind rotate its wake rotation larger. Okay? So, because of Newton's third law, we have this type of behavior where in the ideal world, where omega is really big and Q is really, really small, then my wake isn't rotating at all. And if this is my bet, so this is CP, and this is my Betz limit, and this is my tip speed ratio, which remember is capital omega R, big R, the radius of my blades, over U infinity. When this tip speed ratio, when these blades are moving really, really fast compared to the wind speed, that means omega is big and Q is small. So I'm going to be, I'll be here. But when my tip speed ratio is small, it means that to get the same amount of power, my torque needs to be big. And which means that if my torque is big, that means I am imparting a lot of torque also onto the wind, which is going to cause that wind to rotate. Okay? So we want to design our wind turbines. If we want them to be efficient, we want them to spin really fast compared to the wind speed. So we want them to be high speed, low torque for efficiency. And what I'm going to do now, and so this is what we said before where our maximum, by the way, this is maximum CP. What we did before was assuming that we had no wake rotation. This is considering wake rotation. And what I'm going to do now is mathematically derive this curve. And we're going to go through this. I think it'll take about a half an hour, which is less time than we spent last time. But I want to warn you that the derivation we're about to do, I consider to be more on a low-end graduate student level. Okay? So I'm not expecting you guys to follow every single detail of this derivation. All right? I just want you to get the gist of it. And I want you to know, I want you to understand the repercussions of the results. Also, I want you guys to get a little bit comfortable with doing this type of math because we will need to think sort of like this, but not in as much depth as I'm going to go into to do blade element theory that we're going to look at next week. Alright, alright, so we're gonna do the same thing we did before when we were looking at axial flow. I'm gonna draw a control volume. The difference, however, is that, so here's my rotor, that I can't treat the entire rotor as one control volume. I have to do this axially. So what we're gonna have to do is we're gonna have to look at what, donuts? Annular discs? What's that shape called? We're just looking at, so this is my control volume. This is like the entrance to my control volume. Annular, there we go. And so, actually the way, I should actually draw this, so I'm gonna say my blades go out here. So this is our control volume. Our control volume, so this distance from here to here is big R. This distance from here to our particular control volume is R. Here we have dr. Okay, in our control volume. So we're going to have, again, if I this is our, I've got some, this is looking at the plane view of the rotor. So this distance is R. This distance is dr. Okay? All right, and we're going to have to then do this, and then we're going to have to integrate over the entire disk.
Quick question.
Yeah.
Does big R and little r increase as you get closer to the rotor, or is that supposed to be constant?
Big R is a constant. Big R is the we're going to look at this annular, this little dr, and then we're going to have to integrate from R equals 0 to big R dr.
Okay, so it's constant no matter where you are with respect to the turbine or to the propeller or the rotor. Because it looks like
big R is the length of a blade.
Oh, okay.
Okay, so big R is the length of the blade, and little r is some arbitrary, it will change in, we would be integrating over it, right? We're assuming this dr, what, is infinitely small, right? And we're going to integrate over dr to get what's going on through the entire rotor. So what we're going to do is we're going to develop formulas for a differential thrust and differential torque, and then integrate over the entire rotor. You got that? Does that make sense now?
Yeah, thank you.
Okay. All right. So, all right. First up, we're going to look at this annular ring, and I can look at Bernoulli.
Where is he?
But over the annular ring. But now I'm looking not at my axial velocity. I'm going to be looking at the kinetic energy in my rotational velocity. And what I'm going to get is my pressure. Remember, this is my plus side and this is my negative side. Pressure on the positive side plus 1/2 rho capital omega squared r squared. Remember, so at the angular disk, this is the rotational velocity of the wind. it's the rotational velocity of the blade. But from the wind's point of view, because the wind up here is straight, is coming in straight, and the blade is rotating, the relative wind velocity is in front of the turbine is capital omega squared r squared. And this has to equal the pressure on the other side plus 1/2 rho the velocity of the turbine, of the blade, plus the velocity of the wind. All right, so what I want to do here, and I'm going to skip all the math. I want to get the pressure terms on one side, and I want to get the kinetic energy terms on the other side. I'm going to FOIL this out in my head. I FOILed this out in my head. When I FOIL this out in my head, I'm going to get a 1/2 rho omega, capital omega squared r squared on both sides. I'm going to get little omega squared. And I'm also going to get a term 2 omega, capital omega times lowercase omega. Okay? The two capital omega squares are going to cancel each other out. Okay? And so what I'm going to end up with, and you can prove this to yourself later if you don't trust me, I'm going to get the change in pressure equals rho capital omega plus 1/2 lowercase omega, angular velocity of the wind, times omega, angular velocity of wind, r squared. Okay? And I'm going to call this equation 1. Now I'm not interested in the pressure difference, I'm interested in the thrust. So the thrust on the blades, and remember it's the angular thrust. So the thrust, remember my dA, my area, the area of my angular, my angular disk or my angular ring is going to be 2 pi r dr. And my thrust, is going to be my change in pressure times dA. So this is equal to rho times angular velocity of the blades plus 1/2 angular velocity of the wind, times angular velocity of the wind times r squared times 2 pi r dr. Now, I've got a lot of little omegas here. I'm going to call this equation 2. Okay? Now, I'm going to introduce the angular induction factor. And it's going to be defined a little bit differently than we defined the linear induction factor. This is omega, little angular velocity of wind, over 2 times the angular velocity of the blades. Then what I'm going to do is I am going to replace all the little omegas in this equation. I'm going to replace with 2 big omega A prime. When I do that, I am going to get equation 3. It's a definition. So my dt is going to be equal to 4 A prime times 1 plus A prime times 1/2 rho capital omega squared r squared 2 pi r dr. And I'm going to call this equation 3. Now, previously, on our last episode of wind energy engineering, I said that our thrust could also be written as 4A, where A is the axial induction factor, 1 minus A, 1/2 rho u infinity squared 2 pi r dr. Right, and so I'm going to call this equation 4. All right, so actually I didn't say that, but I defined thrust for the entire for the entire rotor, and now I'm just saying, well, this would be the thrust for just the angle. All I'm doing is replacing the area, the entire area of the rotor with just the area of our angular disk. Okay, so shouldn't be a big surprise. The next thing I'm going to do is I'm going to take this and I'm going to make it include this. And I'm going to skip a bunch of algebra, but you can see that the 2 pi RDR, that's going to get canceled off both sides. And also, well, the half and the rows. And I'm going to end up with an expression, A, 1 minus A over A prime, 1 plus A prime, yes, is equal to omega squared, lowercase r squared, over the upstream wind velocity squared. And I'm going to, actually, I'll hold on to the back there. I'm going to tear this piece of paper off because I want to type something. All right, so I am going to define previously I defined lambda as my velocity of my blades, angular velocity of my blades over or times the length of my blades over the axial wind speed. I'm now going to define my local tip speed ratio as the angular velocity of my blades times the radius that I'm at now, the local, for some distance r along the blades, over the wind speed velocity. And therefore, I can write this as my local tip speed, my local speed ratio squared. Also, I can look at this and realize that I can also define this term as my tip speed ratio times the ratio of the radius I'm interested in right now over the total radius. All right. Oh, and this is important because we're going to use this equation a lot later. So this is equation 5. Okay, and equation 5 is going to come up in a little bit. We're going to set equation 5 to the side right now. Now, what about my torque? I want to find my applied torque on the annular ring. This will be dq, not Dairy Queen. Okay? And dq is going to be the differential of the mass flowing through times the angular velocity of the wind, which the angular velocity of the wind times r, so the actual rotational velocity of the wind, times, and this will have units of force. Whether this is velocity, and then I've got that mass flow rate dt, and I'm just moving it over here, so this will end up being units of force with a dt from that. And then I need another r, because torque, remember, is the units of a moment. So it's force times distance from its the rotational center. Okay. My differential mass, this is going to be rho u 2 pi r dr. That's my mass flow rate times omega r times r. All right, so now I've got a little omega here, and I've got this is the velocity at the rotor. Okay, so now I'm going to use my definitions that A equals u infinity times 1 minus A, and A prime equals, I forgot where the 2 was. It was omega over capital omega, and was the 2 on the top or the bottom? I don't know. Bottom. Okay, so I'm going to plug these definitions in here, so I can write everything in terms of capital omega and u infinity. And what I'm going to get is dq is equal to 4 a prime 1 minus a 1/2 rho u infinity capital omega r squared 2 pi r dr. Right? Now power, oh, I should probably, this was equation 6 and this is equation 7. Okay? Now, power. Power, remember, is my torque times my rotational velocity. So my d power is just this expression times this. Which I think I called this equation 8, so this is equation 9. So now I'm going to remind myself that I define lambda r as equaling angular velocity of my blades times r over u infinity. So therefore, I can define r as u infinity lambda r over omega. And everywhere I see an r, a lowercase r, I'm going to replace with this expression. Okay? And so what I will get is equation number 10, which is my differential power. So this is the power that's generated from this particular annular ring, is equal to 1/2 rho a u infinity cubed. Now that looks interesting. 8 over tip speed ratio squared times a prime 1 minus a lambda r local tip speed ratio, local speed ratio cubed d lambda r. All right. Hey, my definition of my power coefficient was equal to my power over 1/2 rho a u infinity cubed. So therefore, if I put a d in front of my power and I put a d here, I can say that kind of like my local like the power coefficient locally at this particular distance r, at this particular annular ring, is simply equal to, I have to make myself write out this expression. Squared a prime 1 minus a lambda r cubed. And therefore, I can say that Cp is equal to 8 is a constant, my tip speed ratio is a constant, so I can pull this out in front. Integral from 0 to lambda a, oops, make it really clear that's an a prime 1 minus a lambda r cubed d lambda r. And so now I have an expression. I have an expression for my power coefficient, my efficiency. Which remember, that's what we were trying to do. But I'm not done yet. I have 10 minutes left of class. All right. Problem with this is that I am integrating with respect to lambda. But a and a prime are variables. So in order to carry out this integration, I need to relate a and a prime to lambda, r, to the local speed ratio. Okay? So I need to come up with these relationships. All right, so I said a while ago that equation 5, we're going to set it aside. And that we'll come back to it. We're going to come back to it now. Okay? So notice that this is a relationship that involves both lambda r, a, and a prime. All right, so that's going to help us. All right, so I'm going to solve. So I better give this equation a number. It seems kind of important. So this is equation 11. Okay, now back to 5. Solving 5 for my angular induction factor, I'm going to get a prime is equal to negative 1/2 plus the square root of 1 plus 4 over lambda r squared, a 1 minus a, okay. Now, if I look at 11, which is the equation I derived right before this one, it's pretty clear that this is going to be maximized when this expression is maximized. So I need to find the maximum of this expression. All right, and so this is, oh, this here. This is 12. And the next thing I'm doing, I'm going to take 12. Right, okay, so I'm going to call this expression prime 1 minus a. I'm just going to call this expression 13. And I'm going to plug 13 into 12. Take derivative. This is the part that I was like, this is kind of beyond what I expect undergrads to do. So this is just accept this. I'm going to take 13. I'm going to plug it into 12. Then I'm going to take the derivative and set equal to 0. And what that'll give me is lambda r optimal squared. Sounds like a transformer. 1 minus A, so this would be A optimal, which by the way, I know what A optimal is, right? All right, I know what I think it should be. It should, ideally, it should be 1/3. Minus 1 squared over 1 minus 3A optimal. Okay, I'm gonna put a big red box. This is equation 14. I'm gonna box around it because it's an interesting equation. It's an interesting equation. For one thing, what it tells me is that if my A optimal is 1/3, which is what, well, in the derivation of the Betz limit, we found that A optimal was 1/3. Now this is, it'll only be 1/3 if there is no weight. But it tells me that if there is no weight, then my A opt I know is 1/3, I'd have 1 minus 3 times 1/3 is 0. And so what I'm seeing here is that in order to be at my A optimal, I need my local tip speed, my local speed ratio to be infinity. Okay, so it tells me that when this is infinity, I will be at my A optimal. Okay. All right. I take 14 into 5, and I will find that A opt my local my angular induction factor optimal is going to equal 1 minus 3 A opt 4 A opt minus 1. And again, I want this to be 0, right? And this tells me that my angular velocity of my wind in relationship to the angular to the angular velocity of the blade, I want this to be 0. And it will be 0 when my angular induction factor for the axial velocity is 1/3. Okay, and this is now equation number 15. We're almost done. So I differentiate 14. Why do I need to do this? All right. Differentiate 14 with respect to A, and set to 0. And what we're going to get is that a relationship between d lambda optimal and dA optimal, which is what we wanted. So we end up with a 2 lambda r optimal d lambda r optimal is equal to 6 times 4A optimal minus 1 minus 2A optimal squared, let's put it in here, divided by 1 minus 3A optimal squared dA optimal. And that is equation 16. Oh, I've got 1 minute left. Let's see if I can do it. All right, so finally, that tells me I can get CP max. Now, as a function of lambda, I'm just going to say this. Oh, it's actually, I should. All right, to get this, I'm gonna integrate 11 under condition of max CP. So I'm trying to maximize this, and I'm gonna substitute 14 through 16 into 11. And remember, 11 was my expression for CP. And what I'm going to get, finally, and hopefully the camera won't focus me on as I say it, is CP max is a function of lambda, my tip speed ratio, integrated from A1 to A2. You're still there, okay. 1 minus A, 1 minus 2A, 1 minus 4A, over 1 minus 3A. All of this squared dA. Okay, and where A1 turns out to be 0.25, and A2 is determined by when I need lambda r, because I'm really integrating over lambda. So I need lambda r to equal lambda at r, and we can use 14 to solve for this. The results, and I'm just going to show you this page, and I'm going to post these notes just after class. So the results are for various values of your tip speed ratio lambda, you can directly solve for your upper limits of that integral and get different values of CP max. And you can numerically, therefore, find this curve where your maximum possible power coefficient turns out to be a function of your tip speed ratio. Now I want to know, this is your maximum possible tip speed ratio. Your actual wind turbine that you design, it'll have some tip speed ratio where it has its highest efficiency. And that's going to depend on how many blades your turbine has and how wide those blades are. Because remember, what you want is you want your rotor to be spinning fast enough that each particle of wind sees a blade. So your blades are really wide, it'll see the blades. If the rotor is spinning slowly, which means it'll have a low tip speed ratio. Or if you have few blades and they're very thin, the motor will have to spin very quickly, okay? But what you end up with then is if you design your wind turbine with a low solidity, there's very, like 1 or 2 or 3 blades and they're very thin, then you will have a power curve for when you compare your, what's called a lambda CP curve, with a particularly high optimal tip speed ratio. Whereas if you design your wind turbine to have lots of blades and have low torque, or therefore have high torque but low speed, you will have a lower power coefficient, and it will be less efficient, but it'll create more torque, which might be what you want. Or you could just design it to spin really fast and put it in a gearbox to get the torque. All right, I know I went through that pretty quickly. And I know I am out of time, and I know we're past 5:30, and President can't keep that up. I apologize for all the technical difficulties. I also apologize for going through that pretty quickly, but again, I just wanted you to get the gist of like the big picture, okay? And have a good weekend. And do remember, when you guys fill out your teaching evaluations at the end of the semester, that the technical problems are not my fault. Alright, have a good weekend, guys.
Oh, yeah, I'm just not
So it's like 0 to 2, 2 to 4, 46 and all that, right?
Yeah.
So then
If you want the.
I mean, we can move if we need to.
Bye, thank you.
Yeah, let's try one of the small ones. So they make Christian.
Yeah, gotta go. Good night, guys.
Professor, other left their keys, over left their keys, crap. Is that Caitlin?
No, I don't know his name.
I didn't even look.
I know what it looks like, but I don't know.
Somebody,
Yeah, someone left their keys. Hold on, they drive a Toyota
Oh, it's that brown Toyota, in front of Christian.
or a Honda. So I just walk out holding them out.
Alright, have a good weekend.